Alright, in this video I'm going to be talking about detecting convergence or divergence when using a root finding method. So the root finding methods that we've talked about so far are bracketing methods, and open methods. These are kind of the two classes of root finding methods. And specifically we've talked about the bracketing methods of, if we were to make this a little table here, let's see here, we had the bisection method and false position method, and then the open methods we had the Newton-Raphson method, and also the secant method. Now, bracketing methods assumed that we specified some bracket that had an x lower and an x upper that bound a root, right? So, for example, if I had some interval, this is x, this is f of x, and some function that has a root, right here, right? That's the root. And we provide some bound, some interval x lower to x upper, right? And we assume that inside this interval there's exactly one root. And if that's the case, then bracketing methods always converge. So bracketing methods provide guaranteed convergence. So guaranteed convergence. That means no matter what, they're always going to find the root. Okay? We don't even have to worry about whether or not they're going to find the root. But for open methods like the Newton-Raphson method right here and the secant method, these methods do not provide guaranteed convergence. In fact, they don't always converge. And whether or not they converge depends on, let's write this down. So convergence depends on the function. On the function that you're searching for, in which you're searching for a root, and your initial guess. So, for example, let's come down here and draw another little diagram. If I have some function, say it looks like this, let's see. Okay, so here's my root right here. Okay, this is my root where it crosses the x-axis. So this is x, this is f of x. Then let's say we give it an initial guess right here. Call this our first guess, x1. Let me let's draw this function out like this a little bit more and see if I can erase this. Hold on, let me just increase my brush size here. Decrease brush is D, increase brush O is F, that's what I thought. There we go, okay, now I can erase this. Alright, sorry, I'm still learning how to use my software here. Alright, and let's make this smaller again. Okay, there we go. Alright, so if we were going to make this our first guess right here, the root finding methods look for a root by drawing a tangent line to the function and finding where that tangent line crosses the x-axis. This would be x2. But the way I've drawn this here, you see this has come to a point where we've got pretty much a zero slope. So where does the tangent line look like here? Well, it looks something like this. We could draw this, and maybe it crosses the x-axis somewhere way out here. So crosses x-axis way far away from the root. And so that's a case where you would get divergence. So when you run into a case like this, where one of your guesses lands on a place has zero slope or very close to zero slope, you're going to get sent far away. Now, the method could recover and then start to maybe this function goes off to negative infinity. Okay, maybe it goes off to negative infinity, and if it does, then eventually if it wasn't a zero slope but it was just close to zero slope, then what's going to happen is it's going to shoot off way out here, and then it's going to climb up this hill slowly and eventually get back to here. That's going to take it a long time to get back. But it could be that this function does other things, has other points of zero slope and whatnot. Depending what the function does, it might, when it's climbing back here, hit another point of zero slope and get sent off in this direction or way off. So way off in this direction or way off in the other direction. And you might never come back and find this root. So we need to be able to detect when that's happening when we use an open method. And typically the way that we detect convergence for open methods is the same as the way we do with bracketing methods. So detecting convergence, convergence/divergence. The way we do that is we typically measure the error. So we can use approximate error. So what we can say is if the absolute value of the approximate error gets smaller, we could use the approximate error, or actually what's more commonly used is the percent relative approximate error. If this gets smaller as we iterate, smaller, then we assume we are converging. However, if it gets bigger, so if approximate error or percent relative approximate error gets bigger as we iterate, then we assume it's diverging. Alright, let's do like an actual numerical example. Okay, so let's pretend that we're using like the Newton-Raphson method to find a root, and we get this little table of data. Let me build this little table here for you. Alright, let's build a little table. Now let's label this. This will be the iteration I. So I stands for iteration. Xi is going to be the x value at that iteration, and we'll just calculate the approximate error at each iteration. Okay, we'll do this, and we'll say, let's see, I'm 1, 2, 3, 1, 2, 5, so something like this, and this, and this, and this. There we go. Alright, so this is iteration, this is our initial guess, so we'll call 0 our initial guess, our first iteration, second iteration, third iteration, fourth iteration. So we start out our Newton method or secant method with a guess of 5. Okay, we'll say that's where we think our guess is, and we can't calculate any error for our initial guess because we don't have a previous guess. But after we calculate our first guess using a Newton-Raphson step or a secant method step, we could get something like this. Maybe it's 5.11 is our next guess. Now we can take the difference between these two and the absolute value of that difference and calculate an approximate error of 0.11. And then what if the next value was 5.18 and then 5.26 and then 5.35 . Well, we could calculate errors for each one. So the approximate error for this iteration is the difference between this value and this value, which is 0.07. Well, now just looking at this, we could say, hey, after the first two iterations, our error is getting smaller. It went from 0.11 to 0.07. But let's keep going. Let's see what happens. If we calculate here, we get 0.08 and then 0.09. Okay, it's not going down anymore, it's going up. So is this converging or diverging? So I would say that the overall trend is that it's going up, because if I was to plot this error versus iterations, so this is plot, this is our initial guess, this is 0, this is iteration 1, so this is iterations, and this is the error, the absolute value of the error. 2, 3, 4. Okay, we start out at an error of 0.11. 0.11. Okay, so something like this. And then it drops all the way down to 0.7. Goes down. And then it starts to climb again to 0.8. 0.9. Oh, did I get that wrong? 0.7, 0.8, 0.9. Oh. My problem is we can't calculate an error for this first iteration. We can calculate it here. So for iteration 1, that's our error. Then we come down here and go 0.7. Okay. Iteration 2, 0.8, and 0.9. Okay. 0.8, 0.9. This obviously isn't a very good plot, but you get the general idea. So the error initially goes down, but then it goes steadily upward for several iterations. And so I would, just by looking at this, my judgment call would be therefore this is diverging. Diverging. Okay. All right. Another thing that we could measure instead of the approximate error or the relative approximate error is we could just check the function itself, the absolute value of the function. So if this is x and this is f of x, we could plot the absolute value of f of x. Okay. So maybe on iteration 1, the absolute value is some number here, and if this number continues to go down, sorry, this should actually be iterations here. Iterations. If it continues to go down, we would expect it to go down until it started getting close to 0, where this is 0, right? And so that would be converging. However, if instead of going down, it went up, maybe it went down a couple times, but then it started going up, we would say that this is diverging. So the absolute value of the function tells us how close the function is to actually being 0, which is, we want it to be 0. We want to find the x value where f of x is equal to 0, right? If our function goes like this, and crosses the x-axis, we're looking for this point right here. So if we track the absolute value of the function, then what we're doing is, if I was to plot the absolute value of this function, it would look something like this, right? Because over here where it goes negative, if I take the absolute value, it becomes positive. And so the Newton-Raphson method and the secant method can jump around. First guess might be here, then next guess might be here, then here, then here, then here, then here, then here, here, getting closer and closer to the root. But the idea is the absolute value might start, the absolute value of the function might be here, then it might be here, then here, then here, then here, here, here. You see that the absolute value is actually going down, right? Whereas if it was going up, then we would say it's diverging. So those are just kind of the two general ways that we track convergence for open root finding methods. Bracketing methods, we have guaranteed convergence so long as we can find an interval that brackets a single root. So let's just kind of summarize this. So when to stop, stopping criteria. It's the same for bracketing bracket methods. We use the error. We continue until a specified error criterion is met, and if it gets smaller instead of bigger, then it's diverging. Alright, we'll call that our end of our video, and we'll see you in the next one.